this video, we're going to show you how to convert AC to DC current and use it to power up an LED. Alright, and let's go ahead and jump into some notations. And starting from the top, we have our DC source, and what a DC source basically is a battery. And we represent that with a circle with a plus and a minus. And if you notice next to the DC source writing, we have plus and a minus, and what this represents is that this component is polarized, and the direction that it's in your circuit does matter. And moving on, we have our AC source, and we represent this with a circle and a sinusoidal inside. And what AC source is it's alternating current, so it alternates from positive and negative voltage. And places where you can find AC sources are the outlets within your wall. And continue on, we also are using diodes in our project. And what a diode is it only allows current in one direction and allows very little in the opposite. And how we represent this is with a triangle and a line. And just like the DC source, this component is polarized, with the anode or the positive on the flat side of the triangle and a cathode, the negative, on the line side of the component. And for diodes we're going to be using, our cathodes can be represented by the silver line and anode on the other side. And moving on, we are also going to be using resistors in our circuit, and refer to your resistor color codes on how to read the resistor. And for this component, we represent it with sort of a sawtooth symbol. And then we're also going to be using capacitors, and we represent that with a line and a curved line. But in some circuits you also see two parallel lines, and that still represents a capacitor. But for our capacitors, we're going to be using an electrolytic capacitor, which is polarized compared to ceramic capacitors. And how you read the negative side on the circuit is with the curved line, and on the actual capacitor itself, the negative lead is normally shorter, and the negative side also has a silver line on it. And continue on, we are also going to be using LEDs, and the LEDs represents light emitting diodes. And what light emitting diodes does is they emit light, but because they're also diodes, the symbol is similar. The only difference is you have two arrows coming off it, and the arrows represents light. And on the actual component, you can tell which side is the cathode side by the shorter lead or by the flat side looking at it from a front view. And then we're also going to be using transformers in our project, and what a transformer does is it transforms AC current to a different voltage. Say for example you have an input AC AC voltage of 120 volts, and in the first coil you have 10 coils, and in the second coil you have 1 coil. So that's a 10-to-1 ratio, so it's a step 10 transformer. And what it does is it'll convert 120 volts to to a 12 volts AC. But if you were to flip that around, it will convert 120 volts AC to 1200 volts AC. So the order sort of does matter with this component. But unlike the other components, this component has four wires, 2 input and 2 output. And refer to your instructions on your transformer for the proper wires. And then before we continue on to the actual build itself, we're going to go into a little bit of theory on how to convert AC to DC. And what we have is, on the left, it's 120 volts AC, and what we want to do to that is convert that to 12 volts DC. And how we're going to do this is, first let's start with what 120 volts looks like. And a notation we did not mention before was the circle with a V. And what this is a voltmeter, and what it does is it reads the AC current, which you can see on the right. And what we have is 120 volts AC, but that's not what we want. We want to first convert that to 12 volts AC, which we do by adding a transformer. And we're using a step 10 transformer to bring the voltage down 10 times, so from 120 to 12 volts. So right now you can see on the graph on the right we have it at 12 volts AC. But then we're not satisfied with 12 volts AC. We want to have it in a way that we only have positive voltage. Because if you were to look back at the picture again, for like every time it's a negative voltage, there's not going to be any current running through the LEDs, because the LEDs like the diodes only allow current through one direction. So when the current is negative, it's not going to allow anything. So in a way, you're losing half your power each time you're using your LEDs. So what we're going to want to do is convert all the negatives to positive, and we do that by using a bridge rectifier or a diode bridge. And what a diode bridge does is it only allows current when the voltage is positive through one direction, and when the current is negative through a different direction. And they compensate for each other in a way that you only get positive voltage out of it. And sort of to represent the graph, think of it as the absolute values of sinus theta, and where the voltage is always positive. But then this still isn't ideal. This isn't the line we want. This is still moving up and down. And you may say, we have positive voltage, then we can always have that LED. It doesn't matter if it's constant or not. But it sort of does matter. And if you were to look right here, let's say we have a component that only runs on at least 9 volts, and any less it shuts off, and any more it'll be fine, ideally. And if you were to look at this graph, you can see that it's not always 9 volts. And you can see where the squares are orange, that's where the component's going to run, but anywhere else it's less than 9 volts, so the component's not going to run. So it's still going to flicker. But if you're thinking of an LED, the flicker is going to be so fast you can't see it. But then on a power consumption level, you're still losing about half your power, because half the time the LEDs aren't on and they're not allowing the current through. So we're going to fix this by adding a capacitor. And what a capacitor does is it opposes a change in voltage. So by adding a capacitor, we can resist the change in voltage, so it's always a constant line. And because we're using an electrolytic capacitor, this is where we get a positive and a negative DC voltage coming out. But still, this isn't an ideal 12 volts, because what a capacitor does is resists a change in voltage, both voltage gain and voltage loss. So what it does is it takes an average voltage, which we call the VRMS voltage, which is the voltage root mean squares. And how you calculate this is the voltage peak, so the peak of the crest of the sine wave, divided by the square root of 2. And what we get is 8.45 volts, which isn't the 12 volts we were looking for, but 8.485 is probably the more realistic voltage that comes out. And something to look out for is a weird voltage signal. And if you get a voltage signal that looks similar to this means your capacitor doesn't have enough capacitance. And what that does is it resists less change compared to a higher capacitance capacitor. So what it does is it sort of stabilizes the line to a bit, but then not to an ideal line. And to fix that, just go ahead and change to a higher capacitance capacitor. And now that we completed our AC to DC circuit represented on the left, and what we're going to do from now on is we're going to use the symbol on the right as our notation for our AC to DC circuit. And we're going to keep it like that because basically the image on the right is the same on the left if you're looking at through the inputs. You're looking at through the outputs. And for the rest of this video, we're going to go ahead and say that our DC source is 12 volts instead of the 8.5. So then, lighting our LED, to light up 20 LEDs, we calculated that we can have 5 LEDs in series and 4 sets for 20 LEDs. And typical LED operational voltage for white and blue LEDs are between 2.5 and 3. So if we have 5 LEDs in series, that's going to be 2.5 voltage on each, which is about 12.5 volts, which is an ideal case. And putting in LEDs in parallel won't drop the voltage; it will drop the current. And you may be thinking, why don't you have load a current limiting resistor. And the reason for that is since we have enough LEDs in parallel, it sort of splits the current through each set of LEDs, so the current is low enough that we don't need a resistor. And building the AC to DC current, but before we get into that, let's go ahead and talk about the parts that we're going to be needing for this project. And starting out, you're going to need an AC source, which you can get from your outlet, and then you're also going to be needing a transformer. But in our project, in our video, we are not going to be using a transformer. Instead, we're going to be using a Variac transformer, and what it is, it's a variable transformer which we can control output voltage. But if you don't have one, which chances are you probably don't, so what you're going to want to do is to get a transformer and step down voltage a bit. And the transformer we recommend if you're going to be doing this is model number 273-1385B. And what this transformer does, it converts 120 volts AC to 12.6 volts AC. And if you're going to be using another transformer, refer to its manual on its operational load. But then continue on, we're also going to be using 4 rectifier diodes, and our particular model number is 1N4007. But any rectifier diode will work so long as the load current going through it is sufficient for your project. And you're also going to be using a 100 microfarad electrolyte capacitor. We're also going to be using 20 white LEDs, and then we're also going to be using a breadboard with wires. And let's go ahead and jump into it and build our circuit. Alright, let's start out by building our bridge rectifier. And how we're going to have this set up is the red one and these black nodes. These are going to be our AC inputs. And then this red power rail on the left is going to be our one input, and this blue power rail is going to be the other. And let's go ahead and start out by building a bridge rectifier. And if you remember, the side with the silver on the diode is the negative side, and this other side is the positive side. So please refer to this circuit if you can't see the detail in the video. So let's start out by building a bridge rectifier. And you don't need to follow this pattern, but for consistency with the drawing, I'm gonna go ahead and follow the pattern I drew there. And these are the top 2 diodes. Alright, and let's go ahead and connect these 2 nodes together. Alright, and let's go ahead and connect these to our power rails. And from this top node up here, we're going to connect that to one of our AC inputs. And from this bottom node down here, we're going to connect that to our other AC input. Alright, and let's go ahead and move on to the next part. Alright, and if you remember, how we represent our AC circuit is with this DC symbol, because basically the output of the circuit on the left is the same as the output with the circuit on the right. So we use this symbol to clean it up a little bit. And let's go ahead and start by constructing our LED array. And if you remember, the top side, or the flat side of the triangle, represents the positive, and the negative side, which is the other line, represents the negative side of the LED. And let's go ahead and construct our LED. But also remember that the negative side is also the flat end of the LED, and also the short end of the lead. So let's go ahead and start. Alright, and after some time cleaning it up a bit, this is how our final circuit looks. And as you can see, we have our 4 sets of LEDs with 5 in series each. And then we also have our AC to DC circuit right here with our capacitor and our diodes. And then for our AC source, our AC current, we're going to have 12 volts AC going here. And again, if you're gonna have 12 volts AC from your wall going to these two, you're gonna have to run these two into a step down transformer and then back into the circuit. So let's go ahead and test this out with some AC current.
Completed circuit looks as so. Cool.